So we did I think very few problems on simplification. So let us look at some of the problems at the back of the chapter. Okay. Problems. All problems are basically to simplify. Simplify the Boolean expression. Question number 1. This is problem 2.2a. Given x dot y plus x dot y bar. Okay, so whenever you do this simplification using Boolean algebra theorems or postulates, so you mention what step you are taking at each level. So here you can see that x dot is common to both, so you can pull out x dot and write it as y plus. Now this is basically distributive property. And then you can write it as x dot 1. Here we are using complement, definition of complement, and then this is equal to x, where we are using identity element of dot operation. Okay, so that's the simplification. Number 2, look at x plus y dot x plus y dash. So these are two variable Boolean functions. So all of this down the line at different stages, they are all equivalent expression. They all represent the same Boolean function, which is f of x is equal to x. It's independent of y basically. Okay, so now if you look at this one, it's basically interchanging the dot and plus. So in a way it is the dual of the above, but nevertheless let's do it. So x plus is common, so you can pull it out, then you can write the remaining. So this is distributing plus operation or operation with respect to AND operation. So that is basically x plus 0, and that is equal to x. So every step is same. Here we have used a distributive, here we have used a complement, and then again identity element of OR operation is 0. Number 3, x, let me put the dot explicitly, x dot y dot z. Although down the line we may ignore the dot and just simply write like this, x dash y plus x dot y dot z complement. Okay, so if you look carefully at these expressions, sometimes you don't know how to really proceed from the start, how to take the next step. So if you look at y is common everywhere, so you can arrange the expression in such a way that y will come first. So that will be commutative property, x and y or x dash and y you can interchange. So that will be y dot x dot z plus y dot x dash plus y dot x dot z dash. So what I used is basically commutative postulate, and then I can pull out the y dot, and then the remaining thing is basically x dot s, and also let me interchange this x dot z dash. Let me put it first, x dot z dash, then plus x dash. Okay, so here I have used distributive, and also I have interchanged these two positions, so I used commutative again. Okay, so now it is much simpler. If you look at again, inside the two terms, x dot z, x dot s. So I can apply distributive property one more time and get z plus s. Okay, so I use the distributive again. Then y dot x z plus z dash, z plus z dash is 1, and that is by which property? Definition of complement. And then I apply identity property. I have x, and x plus x dash is equal to 1. So here I have used the identity element and definition of complement. And finally I have equal to y, which is again identity element. So something very simple, y. Okay, the expression was just y, but if you look at this, it looks very complicated. So simplification of Boolean expression is a very important thing. Otherwise we would require unnecessarily many gates to implement the given Boolean function. Actually the given Boolean function was y, and if you wanted to implement y, you don't need to do anything. You just connect the output directly from the y input, because it doesn't depend upon x. It is entirely decided by y, which is equal to y. So if you don't simplify, what would happen is you have to have 3 input AND gates, then 3 input OR gates, so which is really unnecessary. Okay, next, a plus b the whole bar dot a bar plus b bar the whole bar. Okay. So here we can apply De Morgan's theorem and write it as a bar dot b bar, and you can apply De Morgan's theorem to the second term also, and you will get a bar, and sorry, a bar bar, that will be basically a, and this will be a dot. Okay, then we can interchange associative property as well as commutative property we can use. So instead of grouping like this, AND operation, we know that it is associative, but not all operations are associative. Okay, for example, NOR operation Nand operation, these are not associative operation, we have to see that. But dot operation and OR operation, that is plus and dot, OR and these two operations are associative. So you can group, instead of this you can group like this. Okay, so you can do that. Okay, so this is basically associative. Then I can interchange these positions. And again I can, so this is basically commutative. Now I can regroup it. Okay. And regroup like this. Dot. Okay. So again I used associative. Now this is basically 0 dot 0, which is 0. So that's from the definition of complement. Complement has to satisfy two property: a dash dot a equal to 0, and the other is a dash plus, which I used here, a dash plus a is equal to 1. And then x dot x is equal to 0, that was theorem 1, so I can say that also. Theorem 1 is x dot x is equal to x, so 0 dot 0 is 0. So this function, if you see, it was basically a very simple function, that is 0. It is a constant. Okay, irrespective of whatever is the input combination of a and b, whether it is 0 0 0 1 1 0 1 1, but it is giving you 0 for all the input combination. So it's a constant. So constant could be either 0 or 1. Okay, so this way you can simplify. Let's try to see questions from 2.3. A B C plus a dash b plus a b c dash. Okay, so show that this is equal to b. Show that this is equal to b. Okay, so this is, you can say, show that ABC plus a dash b plus ABC dash is equal to b. So if you look at b is common everywhere, you can see b. So first thing you can do is basically interchange a and b positions and write like this: b a c plus b a dash plus b a c dash. Okay, so this I have used a commutative. Then I can pull b dot outside. Then I have a dot c plus a bar plus a dot c bar. Now I can combine the first and the last term. I can a dot c plus c bar plus a bar So here I have used, so here I have used distributive, and then I used commutative also to interchange the last term to the second term, commutative, and then I have used distributive. Okay, so now you can see the result coming. So that is B dot A dot 1 plus A bar. Here I have used complement definition, and then A dot 1 is A, and then A plus A bar, so that is A dot 1. So here I have used identity element, so then what else, definition of complement. Okay, then again it is followed by identity element. So writing these steps and giving the reason or the for the step, it may look a little overhead, but do that so that you get practice of it. Okay. Next, question number 6. Show that let's do x y plus x what w is set plus w is set dash. Okay, I'm just dropping the dot here. Dots are there. Dot is here, dot is here, dot is here, dot is here. So now you should know that even if I don't put dot but write like a product, so it implies AND operation. Okay, so show that this is equal to so this is equal to x into w plus y. W plus y. Okay, so you start from LHS. So you can see that x is everywhere. So maybe a good idea to take x out, and then you have y plus w is set plus w dash. Again you can take w. So here you have to use distributive, and then one more time you use distributive, okay. So again distributive, x dot y plus w dot 1. Okay, so which is equal to RHS. So here I am using definition of complement and identity element, the element of dot operation. So this way you can continue to see. Let's see some more example. Okay, let's do. So this is question from section 2.4b. Show that x dash y dash plus z the whole dash plus z plus xy plus wz. Show that this is equal to x plus y plus z. Okay, so how to proceed? So let's apply De Morgan's theorem. So if I apply De Morgan's theorem, I will have x the whole power dot plus z plus x dot y plus w dot z. So here I have applied De Morgan's theorem, and again apply one more time the De Morgan's theorem. So that will give you x plus y dot z plus z plus x dot y plus w dot z. Okay, so we applied De Morgan's theorem the second time. Okay, yeah, so here there is a dash that will not go away. So now I can combine these two. So x plus y dot z dash plus x dot y plus z. So z I can write it as z dot 1, and then I can write like 1 plus z. Sorry, 1 plus w. So here I am using commutative to interchange the term and then distribute. So 1 plus x is basically 1, and z dot 1 is z. So we have so let me just expand this also. X dot z dash plus y dot z dash plus x dot y plus z. So I think this was theorem 2 and identity element. Okay, what we can do next? we are kind of stuck. Let's see, z dash x plus. I hope I have not made any mistake so far. Let me check again. I apply De Morgan's theorem one time, kept all other terms as it is, applied De Morgan's theorem once again. So x plus y I got, fine, else kept it together, and then okay, I think I have not made any mistake. Okay, so this we have to prove that it is equal to x plus y plus z. So okay, okay, so let's do like this. This is equal to, so I am taking this last term z and bringing it here, z plus, and then I have z dot. Okay, I'm just going back. This I have distributed, but now I am taking it back to x plus y. Okay, which is basically this term only, but I changed the order. I put the z first and then I have x dot y. So I just used basically distributive and commutative once again. It's okay, so same thing. And then what I'm saying is that I will further apply distributive property like this. Okay, so I am distributing this plus with respect to dot operation. So I get these two terms, and then I had x dot y. Now, so this is again just a distributive property. So this I have written for both, and then this is basically one dot. So let me just write it as x plus y plus z. So dot 1, so that I am putting it. Multiple things I am doing here. One is I have interchanged the order, so there is commutative. Then z plus z dash, that is definition of complement, that is equal to 1, and then 1 dot something, so that is identity element of product. Okay, all this I have done. Okay, so now again I am changing the order, x plus x dot y plus y dot y plus z. Okay, I just took this here, the second position, and then what I do is write x plus x dot into no, let's do it the other way. Let's take x outside, and then it is 1 plus y plus y plus z. Okay, so what did I do? I combined, this is basically distributive, combine these two terms by using distributive property. Okay, so now we have arrived. So that is equal to x dot 1 plus y plus z, which is equal to RHS. Okay, so it was a little difficult compared to all other problems. We had to really find a way out to finally reach the RHS. So in general, simplification process, sometimes you may get it very directly, easily you will obtain, but sometimes you have to little bit struggle in order to reach the required result or the simplified result. Okay, whatever given was a very complicated expression, but whatever we finally reached is very simple expression, x plus y plus z, to use only one OR gate with 3 inputs. Okay, so simplification is important, but the process of simplification using the steps of using the postulates and theorems of Boolean algebra is not always very clear what step, how to proceed. So we need to figure it out by checking out different possibilities. Okay, even I have gone back and forth here. Okay, I should not have done, for example, this step. Where was it? Yeah. So this step was really not necessary because I had to reverse that step here. I had to come back to this. So this kind of efforts we need to make while simplifying. So sometimes we may get it directly without any unwanted steps, but that is not assured. So that is why we would always seek for some systematic way of simplification. Okay, so it is necessary. So let's do one more problem and then we will go to systematic way of simplification. Okay. So how many problem we did? This first question. Okay, whatever it be. Let's do one more problem. So the problem is A dash. So this is section 2.4 C. D plus C dash D plus B into A plus A dash CD. Okay, A dash B into D dash plus C dash D plus B into A plus A dash CD. So this is the expression given, and if you look at the end of the book, you can see what is it equal to. So this is basically, so I can write it as show that this is equal to B. So this ultimately becomes equal to B, and you can see that B is common here. So I can take B outside and then A dash D dash plus A dash C dash D plus A plus A dash C D. Okay, so what else? Okay, so if you look at term, this and this term a dash and d are common, and c plus c dash, and c plus c dash is 1. So now I am skipping many steps. We can, once you practice it, you will be able to see easily. So this is a dash, d dash, then plus a plus, so c plus c dash is 1, and therefore this is a dash d. Okay, so what are the steps I have done? So let me write what are the reasons. First of all, I used commutative to interchange the order of the term, and then I used distributive for b as well as here a dash d. I used the distributive, and then c plus c dash I said it is 1, so there I used complement definition, and then that 1 dot a dash d, I said it is a dash d, so that is definition of identity element. So many things we did all together, so that reduces the number of steps, but whatever property we have used, you list it. Now again we can repeat, we can combine this and this. The a dash is common, and d dash plus d will give you a dash, so that is b dot. So this looks little simple. Okay, so which you can write it as b. So here what I used, again I used distributive to combine the term, and then after that d plus d dash by the definition of complement, I said it is 1, then a dash dot 1 I wrote it as a dash, so that is identity element. And then that is equal to b. Here also I wrote it as here also I used the property of or definition of complement, then identity element. Okay, so that's it. I would like to end this type of problems. Yes.
In exam perspective, should we write in this way, sir, or we have to show each step?
If you are able to do it, I mean, you can write it in this way also, because to save time, no, you can adopt to this. But initially, when you learn, maybe it is a better idea to go step by step. If you have time, you can do that. But if you have scarcity of time, you can do like this also. But there should be a proper reasoning, you should know what you did. So to avoid mistake, it may be better idea to go step by step, smaller steps. But if you are taking multiple steps, you can show it like this also, no problem.
And sir, about you have written a theorem once, sir. Should we write in exam in this way, or we have to mention the theorem?
Yeah, so if you mention the theorem, that is more good. I said 0.0 is 0, so basically it is the theorem. Theorem 1, what does it say? It says that x dot x is equal to x.
Yes, sir.
And the dual of that was x plus x is also equal to x. So this you can state it, theorem 1 in bracket, maybe you can state it x dot x is equal to x, so that we know which theorem you have in mind. Otherwise, what you say as theorem 1, if in my mind if it is some other theorem, so that can be a confusion. So it will be good wherever you can be more explicit. If time is available, always do that. that is always welcome. Yeah,
Yes,
but
sir.
if there is scarcity of time and you have to just finish the problem, then of course you are welcome to do this way also. Okay, so but should not have mistakes, ultimately that is the thing. Alright, so so before we go to the systematic method of simplification or finding out the most simplified expression, I would like to say one more thing, that is basically extending operations with the to multiple input. Extension of multiple inputs. So we have already seen that x plus y, so that is a two input OR gate. So this is basically OR operation between x and y, but you can extend it to one more input, say z. So what do we mean by that? So it could mean either this, or it could mean either this. Okay, it could mean either thing. So if at all we need to have an operation which involve OR gate with 3 input, okay, so if you denote OR gate with 3 input, we did that in earlier class. So where we have x, y and z, an OR gate with 3 input, if it is a valid expression, that is x plus y plus z, then it has to satisfy this associative property. Okay, that is necessary. So if it doesn't satisfy the associative property, you cannot do that. Okay, so this we have already proven. This is our associative property. And the dual of this is basically x dot y dot z. You can group these two, and then so this is equal to x dot y dot z. So if this associative property is also satisfied, we have proven it in the sense that we have proven only the first one, but the dual of that is already in that proof. Okay, so this is also a valid thing. Okay, so this is valid, so is this. Now the question is that what about other operations? So we don't have a symbol for other operations, like for example Nand operation. We have listed out all the 2 variable Boolean operation. So there were 16 of them, and some of them, if you look at for example x, y, and then we had a function which is of x and y, which is equal to x plus y the whole bar. So 0 0 0 1 1 0 1 1. Now if I do this operation, x plus y is 0 and the whole bar is 1 1 0 0 0. Okay, so since we need a symbol to talk about this operation, we cannot give any symbol. The book gives one particular symbol which I will also use. The OR operation is or the NOR operation. So this is denoted as this way, an arrow like this. So if we use this symbol, just like plus we use it for OR operation, dot we use it for AND operation, this down arrow we are going to use for so let me say that here this is the symbol for NOR operation. Okay, so this stands for the NOR operation. Now the question is, can we have this possible? Okay, so does this exist, or is it correct to use like this? Now if it has to be correct, then as I told you, you should have the associative property satisfied. You should be able to show that. So now I am not sure about it, so I put a question mark whether this is equal to this, and then that whether it is equal to this. So let us check. So to check, so this is the check. We are going to do the check. So we take this one. So what does this mean? This means if I express the NOR operation in terms of the well-defined operations like OR, and complement, I can write it as x plus y the whole complement. X plus y the whole complement. That is what we mean by this grouping. And this again plus z and then the whole complement. Okay, so this is basically expressing the NOR operation symbol in terms of AND operation and complement symbols. Okay, now we can apply De Morgan's theorem. So that is x plus y. If you take complement of this, you will get complement of this dot z. Okay, so that is number one. Number two, we group y and z. So then again use x plus then y plus z the whole bar and then the whole bar. So that is equal to x dot y plus z. So you can see that they are not same. First one is x plus y dot z complement, and this one is x complement dot y plus z. So they are not the same function, they are different functions, and therefore if you try to do something like this, you will get the wrong result. Okay, it depends upon what you do first. Now I should also say what is the first thing. So number 3, let me, so if I don't put any grouping, what does it mean? So this is now going to be defined like this: x plus y plus z the whole bar. Okay, so this is what we mean by a 3-input NAND gate. It will do this operation, which is basically this, which is neither this or nor this. So once the associative property is not satisfied, there is no point in defining or extending the operation to multiple bits. So it will mean entirely something different, and so this is what usually what we get. Like this. So x, y, z, if you give, what you will get is basically x dash, y dash, z dash, or you can say x plus y plus z. Okay. So what was looked like very obvious in the case of OR operation and AND operation is not so obvious when you take other gates or other operations. Okay, so this is one example, and similarly you can take NAND operation also. It also doesn't have any associative property satisfied, so therefore you need to be careful not to make such mistakes. Okay, so if you are grouping, you get something, and depending upon how you group it, and if you don't group at all, what you mean is like this. Okay, so it is better to define these operation in terms of more basic and fundamental operations, which are plus and dot and complement. So these three are the basic operations. Those are well defined in the Boolean algebra, and the whole Boolean algebra require two binary operation and one complement operation. They are well defined. Okay, so that has to be kept in mind. But now another interesting thing is that if you take another example, say example 2. So I am not doing it with the NAND. It is similar. You can use an upper arrow to show a NAND operation. But what is more interesting, maybe x, y, and there is a function x comma phi, x comma y is equal to x y complement plus x complement y. So 0 0 0 1, then 1 0 1. This is called XOR operation. Okay, probably you are aware of it. So wherever it's basically give you output whenever the parity of the input is 1 or odd parity, it gives you output. So here it is 0, here it is 1, and here parity is 2. So which means it is main number of ones is 2, so therefore it is even, so it gives you 0. A complement of this f is called, so this one f1 and f2, we call it as x dot y plus x complement y complement. So this is just a complement of this, and in this case you have just inversion of this previous output. Okay, so this is called XNOR gate, XOR gate and XNOR gate, and they have a symbol also. If XOR gate is denoted like this, and XNOR gate is denoted like this. Another way this operation is specified is like this, and this is denoted like this. So why I am taking this example is, if you take XOR operation and try to do this, then surprisingly this satisfies the associative property. So x, if you do this, and you will see that gives the same answer if you do this. Okay, but these are like some special cases. Okay, so you can show that. So dot y, then not dot, this is XOR y, then XOR of that with z. So that is x y bar plus x bar y like this. Okay, so then what you have to do, you have to basically take the first term and then multiply it with the complement of the second term, sorry, z, complement of the second, plus then complement of the first term into the second term. So that is equal to, so now if I distribute everything, you can see that it is x I dash z dash plus x dash y z dash plus x y dash z plus x dash y dash, oh sorry, I have to do one more thing. I have to apply De Morgan's theorem here before expanding it. So this, if I apply De Morgan's theorem, it will give me x y dash dot x dash y whole dot z. So that is equal to, so this is basically x NOR gate. So if I use the previous result, I can directly write, but let me just show you that. So now I apply the De Morgan's theorem one more time. Okay, so here I am using, here I have used the definition of XOR gate in the first line. This is definition. So here I use De Morgan and then distribute it on the first. Okay, so now if I apply De Morgan's one more time, that is, it will be like this. So this is again De Morgan's. So now I can distribute. So x dash dot x is 0. Similarly, y dash dot y is also 0. So only term that will remain is basically x y is z plus x dash y dash x dash y dash is z. Yeah, so that is the final result. So I used again distributive, definition of complement. Okay, so those two things I used. So definition of complement, where did I use? Y dot y dash is 0, and then 0 is the additive element, so I used that also, identity element. So this is what I get finally. Now if I start with RHS, that is this side, I will get exactly the same thing. So how to show that? So, one thing is just to show it directly. Let me try to show in a different way. Can I try to reach here? Let me try to see. So y XOR Z. So if I can bring in that form, so wherever y XOR Z. Okay. So look at this term and this term. I have x dash in common, and then I have this term and this term where I have x in common. So let me just combine it like this. So x dot yz plus y dash z dash, then plus x complement dot yz dash plus y dash z. Okay, so this, now I can write it as, so what is in this bracket? This is basically y XOR z the whole bar, and here I have y XOR z. So it's a definition. So what I did, so here I did distributive. That's all what I did, nothing else. I just distributed, and then I used the definition of here I use the definition of XOR operation and XNOR operation. So that's what I told you in the beginning. So if you look at here, F1 is x y dash plus x dash y, and similarly F2, which is XNOR operation, is xy plus, and this is basically complement of this. So that also I have shown. Wherever 0 is there, 1 comes. Wherever 1 is there, 0 comes. Okay, so now it's looking good. So if you look at this, first term complement of the second plus complement of the first, second term. So what is that? So that is basically XOR of this with the XOR of that. Okay, so this is our RHS. So it is well defined. Here associative holds. We started with LHS, that means the second term. So whenever we say that, so what we actually proved is this. So if I have 3 inputs, XOR gate, X, Y and Z, then I can write it like, and this is equivalent to X, Y, the result that you get, I associate. So then also I get same expression, final expression, and also this is equivalent to first combine these two, then combine these two. All of them give you same expression, not different things. Okay, all of them are alike. Whereas earlier what we showed with the NOR gate is that they don't give you same result, they give you different result. Okay, here we did NOR gate, with x and y, and then we did another NOR gate. What we get is basically x plus y. What is that? Okay, so which is very different, and similarly here also something else. So they are not same. They are not equal. Whereas here we have all the things equal. Okay, let's take a break. We'll come back after 4 or 5 minutes.